So, office hours, what are we, week 4? We're looking at 2.1, homework mastery questions 2.1, number 12 and number 26. What is number 12? We'll start there.
Calculate the enthalpy of fusion of SO3 from the following information.
Okay, is this, what do we have?
Yeah, so it's two reactions.
Okay.
One is sulfur solid plus O2 gas reacts to make SO2 gas. And the enthalpy of that reaction.
I'm going to put the enthalpies over here because I didn't give myself enough space on that side of the board.
The enthalpy is negative 296.8 kilojoules per mole. And then the second reaction is SO2G plus 1/2 O2G reacts to make just 1 mole of SO3G.
And what's the delta H of fusion? Or delta H at formation?
Oh, it's at formation. Okay.
Yeah, so just delta H of F.
Yes.
Yeah, formation. Okay, and the delta H for the second reaction?
Negative 98.9.
Okay, so what were you thinking? What did you try so far?
I was thinking between using the equation that you use to find like the coefficients, or the one that's the sum of one, but I wasn't sure which one to use in this situation because it's hard to find the specific molarities.
Yeah, so I'm looking at this, and I think we're going to, so there's a couple different things we could look at and consider, right? First off, we could probably just look it up in a book, right? A delta H of formation for SO3 is probably just tabulated. We can look at it and be like, there it is. Right? We don't really need to do sum of products, sum of reactants. I guess the first thing that I wonder is, what does the formation reaction look like for SO3? Right? So this is telling us we want to get the delta H of formation, but what's that chemical equation look like? And then can we find some way that we put these two together, make it? Anytime we're given a target and multiple reactions, my brain immediately goes to Hess's law.
Okay.
Right? So I immediately am thinking, Hess's law, how can I put these together? I honestly think we're just going to add them together.
And switch the...
I don't even think we need to switch anything.
It's just going straight to SO3. Okay.
I don't think we need to switch it. I think it's literally you add those two numbers together and that's the answer.
Okay.
Right. So to put that into context, the delta H of formation, whenever we're doing an enthalpy of formation reaction, that's going to be the pure elements, sulfur solid, plus O2 gas goes to SO3 gas, right? And we want the molar coefficients to guarantee that we only end up with 1 mole of product. So all I have to do is put a 3/2 there, right? Because that'll get rid of my 2 there, and then I'll end up with 3 oxygens.
Okay.
When I look at my chemical reactions above, it's just adding the two together, right? I'm going to end up with sulfur. My SO2 is going to cancel out between them. I'm going to end up with 3 halves O2. So I'm just going to end up with, my delta H of formation should just be negative 296 plus negative 98.9 overall in kilojoules per mole. So we're going to end up with something that's like 394.9 negative.
Right.
Right. And again, like, the funny thing about chemistry to me is the math is never that hard once you see what to do. It's really all about, this is part of why I stress key terms and vocabulary. I don't need to tell you all to go practice your math skills.
Right.
You know, some of my other classes I do, but this class I'm like, no, you're all fine with math. It's those key terms and vocabulary that tell us which math we're going to do. How do we recognize from the context of the problem, like, what's going on? Right? if I just gave you the delta H of formation for SO3, if I just gave you that equation and said figure out what the delta H for this reaction is, that would look like a table lookup problem. I'd go get my enthalpy tables and I would just look it up.
And that would use the sum of equation?
That would use the sum of equation. But if I'm given two reactions, and I can see how those two reactions with their delta H's could be put together, that's looking like a Hess's law problem to me.
Okay.
And so it's recognizing that context. We've got a lot of different ways that we go about getting information, and it's just a matter of which one do we use in this case.
Right.
The switches, the reason we do it this way is, you know, fundamentally it could be, you know, doing sulfur solid plus 3O2 gas to get SO3, maybe that's a hard reaction. I don't know which of these reactions are hard to do in experiments and which are not hard to do in experiments. But essentially you can do 2 experiments and get 3 answers if you pick the right 2 experiments. So you can cut down on your workload.
Right.
Because in this, we're actually getting the delta H formation for SO2 gas. We're getting enthalpy of reaction for the combustion of SO2, and we're getting the delta H formation of SO3. So 2 experiments leading to 3 results.
Okay.
It's kind of neat, but a lot of times in these Gen Chem classes, we are also dealing with the fundamental fact of like, where do these numbers and all the tables come from? How did some scientists originally do this? And a lot of times that is like, the delta H formation for SO3 might not have existed until someone did an experiment like this. So, although, well, let's not get into my details. So that was number 12?
Yeah.
Questions about that?
No.
Okay, let's look at number 26.
Yeah, it's salt precipitation.
Okay. Number 26. What does number 26 say?
Consider a soluble salt in which the absolute value of lattice enthalpy is more than the absolute value of the heat of hydration. What are the signs of the standard Gibbs energy, enthalpy, and entropy of precipitation?
No other detail?
Yeah, that's about it. Just give positive 0 unknown. Okay, wait. Yeah.
No.
Yeah.
Last sentence is always the important one.
Precipitate when mixing 2 solutions.
Oh, say that again. That's
Formation of precipitate when mixing 2 solutions.
That's the important detail. That's like, so this is how everyone gets these problems wrong. Right? That is actually, that last sentence, this is part of why we did this in the warm-up problems.
Right.
Is because that is actually the most important part for getting this right. Because immediately in my head, as you all know, I do it for, I'm just going to pick, I do it for a solid going to an aqueous plus an aqueous. That's just how my brain tends to do it. So if it's soluble in this case, delta G would be less than 0 because we're going to go to products. My delta H of lattice is bigger than my delta H of hydration in this case, so I'm going to switch that. Delta G is negative. Delta H is going to be delta H lat plus delta H hydration. The lattice is positive. The hydration is negative. I do this cartoon thing where I actually make the size of my plus and minus different depending on which one's bigger. So I can tell my delta H is going to be positive in this case, which means my delta S, because of the equation delta G equals delta H minus T delta S. If delta H is positive, delta S, in order to get my delta G negative, delta S also has to be positive. It has to be positive, and T delta S has to be bigger than delta H. But that's a side thing. But this is for the wrong reaction. Right? This is for the solid going to aqueous, not the aqueous. Right? Our thing that we want to be doing is aqueous plus aqueous goes to solid. What that means is all of my answers are off by a negative sign. So my delta G is going to end up being positive, my delta H is going to end up being negative, and my delta S is going to end up being negative. And I always do it that way. Well, for the last week, I've decided this is my new favorite way to do it. I just figured this out recently. I can't believe I've been doing it different ever. Because I used to actually try to get everyone to remember how the signs flip, and I'm like, wait a minute, why would I do that? Right? I always thinking about, like, I just have this one system I know how to work with, and then I just check, is that the way it is, or do I need to flip everything?
So I guess the question would be, if you're operating under the solid to aqueous, how do you get the values for G and H?
Okay, so for G, it is happens or doesn't happen, right? So we've got a solid. Does it become soluble? Does it become ions in solution? If the reaction goes towards products, negative delta G, spontaneous. So as soon as I see that it's soluble, it's going to ions, that's negative delta G, it's aqueous. Then for the delta H, right? This is a weird part. When we think about how this is thermodynamically happening, it kind of goes back to the Hess's law thing we were just doing. We think about it in terms of 3 steps, but since we're always using water, we can do it in 2 steps. Break apart the lattice, surround the lattice ions with water. Breaking apart the lattice is always endothermic. We have to put energy into making that happen. So for this solid breaking apart, delta H of lattice is always positive. I don't know how big it is, but I know it's always positive. My delta H of hydration, getting that ion-dipole interaction back, that's always negative. I don't know how big it is, but I know it's always negative. So the problem tells me the magnitude of the lattice energy is bigger than the magnitude of the hydration energy. So I know that this positive is bigger than that negative. And I literally draw it with a cartoon where it's like I draw the bigger one bigger and the smaller one smaller. And then I do big plus with small negative, smaller plus. Whereas if I draw it differently where it's like a big minus with a small plus, smaller negative, right? But I can tell because of this information about the lattice energy and hydration energy that the delta H has to be positive. Then I can say, okay, if the delta G definitely ends up negative because we literally just watch it happen, and the delta H ends up positive because of this, probably experimentally we would measure it, but because we've got this data, I need to subtract enough away from that delta H that we get negative. So that means I need this whole T delta S term to be negative, which means delta S still has to be positive. Otherwise, I'd be doing 2 positive things and it would never get to a negative. And again, we can add this extra detail that T delta S has to be greater than delta H. It doesn't often ask for that detail. The thing that asks for every once in a while is when does T delta S equal delta H? When does delta G switch from being spontaneous to non-spontaneous? When is delta G equal to 0? But it's just interesting to think about. That T delta S has to be bigger than delta H. Otherwise, we'd never get delta G to be negative. Now, that was all for the solid going to aqueous. Fundamentally, we say, oh, we want to do the opposite process. I'm going to flip my products and reactants. Sign flips, sign flips, sign flips. I just flip all my signs. We can also make sense of it from the practicality. If it's soluble, it's going to stay as the aqueous ions. It's going to be reactant favored, non-spontaneous. That would be a positive delta G. As soon as we do that, we're kind of like, we can see how everything flips. The delta H in this case is I'm taking the water away from the ions and forming the solid. So my hydration becomes endothermic and my lattice becomes exothermic. I flip the signs of those 2 things, which means this becomes a big negative, that becomes a small positive, the thing is overall negative. Overall negative. Delta S, weird one to think about experimentally, right? Especially with these ion cases, we always think a solid going to, a solid going to a liquid would be an increase in entropy, but we're not just doing a solid going to a liquid, we're doing a solid going to an aqueous solution, which means we've got this water organization, this solvation shell around the ions, which is increasing entropy and then decreasing entropy. And we don't know which is bigger, which is smaller in that. So we have this kind of inferring it idea.
Okay, thank you.
Hey, you bet. Questions?
Yeah, I guess I got here a little late, but I also had a question on 12.
Sure.
Wasn't
Quick clarification. The problem we just did was 26 on 2.2, not 26 on 2.1. We're doing that next. Okay. We're back at it. 2.1, number 26. Can I get someone to read that? Or did you want to do that one?
Yeah. So it says when 25 grams of CH3COOH, that's methane, right?
Acetic acid.
Oh, acetic acid, my bad. Okay. So 25 grams of acetic acid is combusted in a sealed calorimeter, sorry. It releases enough energy to heat 5.30 liters of water from 17.9 Celsius to 29.3 degrees Celsius. And then part A says to use this information to calculate the molar enthalpy of combustion for acetic acid.
Mm-hmm.
And then part B says to determine the final temperature if 1,250 milliliters of 25 degrees Celsius water.
Wait, 1,000.
250 milliliters of 25 degrees Celsius water is heated by combusting 4.9 grams of acetic acid.
Okay. Whew, that's a whole lot. So this is essentially continuing our calorimetry work, looking at combustion. We've got to do the same thing that's always difficult in chemistry problems. We have to figure out, like, what the heck are we supposed to do? Writing out part B, I kind of filled up the board already. But right away, what can we tell? Right, practicing that same thing that we said was always difficult from the context of the problem. I got a delta T.
Yeah.
What does that mean I'm going to use?
Just Q and
Yeah, we're going to use a Q equals MC delta T. I'm also being asked to find a delta H of reaction, so what else am I going to use?
Q and delta H.
We're also going to have a Q equals N delta H. Right, and so this is a sealed calorimeter where we are burning acetic acid in 5 liters of water. So it's just those two things. They're going to be in thermal contact with each other. They're going to be equal and opposite to each other. I'm going to end up with MC delta T equals negative N delta H. Where then I say, okay, which things do I know? Well, I've got my T final and my T initial, so I've got that. It's water. I've got the heat capacity for water is 5.3 liters. That's going to be 5.3 kilograms or 5,300 grams. And I've got my acetic acid, which I can turn into moles. The only thing I don't have is delta H. So at that point, after recognizing that it's, the context of whenever we've got this changing temperature thing, it's almost always an MC delta T problem. And by practicing vocabulary and kind of that context of problems, right, this is the hardest thing. It's like we've learned all this chemistry. Which equations am I applying in this case? So in number 2, it's actually going to be the exact same thing. We're going to have an MC delta T equals an N delta H. Where in this situation, we know the water, we know the heat capacity. We're going to say we know the delta H from before. We've got the N. The delta T becomes the thing that we don't know. So it's actually doing the same problem twice and just changing what our unknown is. I forgot a negative sign. Don't forget your negative signs. Everyone who talked to me about last week's quiz yesterday in office hours, every problem they got wrong was because they forgot a negative sign. And so their temperatures kept going down instead of up. So that's the conceptual work, right? At this point, it's kind of plug and chug. We're still going to do that together, But this is where I think your study time is more valuable, right? Doing that, like, we're pretty much done with the problem. It's still, we got to do the math for it, see what our reasonable delta H, a reasonable delta T. Notice I'm burning like 1/5 of the mass with about 1/5 of the water. So instead of going up by, so I think it's going to go up by about the same amount. It's going up by, that's a 29, right? That's a 9?
Yeah.
Okay, so it went up by about 12 degrees. I think it's going to go up by 12 degrees again. I think it's going to go from 25 to 37. So just by guessing, my guess for T final is 37 degrees Celsius. It's nice if you can start to develop a conceptual kind of process like that. Right? How did I get that 37 degrees? Did that make sense to you? I did it pretty quick. Right? I looked at the ratio of mass to water. And I said, look, with that mass and that amount of water, it went up by 12 degrees. It's pretty similar ratio of mass to water. I think it's going to go up by 12 degrees again. My delta H, I'm expecting a delta H somewhere in the kilojoules range. It's a combustion reaction, so it could be acetic acid. It's a hydrocarbon. I'm just from my experience of doing a bunch of these problems, looking at a bunch of these tables, I'm going to guess a delta H of reaction someplace in the range of 50 to 100 kilojoules per mole. I think it's going to be closer to like 100, but that's my guess range. So again, I'm going to guess. Right? And that's all just from conceptual work. That's the best thing you can do for studying. You're all fine at using your calculators. You're fine at punching numbers in after we get to this point. This is the harder part. But still, let's go ahead and get the answers. I'm going to erase this thinking work now. We're just going to plug in numbers. So we're going to have MC delta T. We're going to have 5300 times 4.184 times 29.3 minus 17.9 is equal to negative 25 divided by, gotta get that's 12, that's 24, plus 32, plus 4, divided by 60. Right, my mass divided by my molecular weight times delta H. Let's go ahead and do some math. 5300 times 4.184 times, whoa, that was a big number. 29.3 minus 17.9. Jeez Louise. 252797. Did I miss a decimal point? I think I missed a decimal point someplace. We'll check in just a moment. Is equal to negative quantity 0.416 times delta H. Is anyone else punching this in their calculators? Can someone else punch this in? I think I made a typo. That number, I think I'm off by a factor of 10 someplace. I'm going to redo it as well to see. No, I got the same thing again. 252797. Jeez.
Yeah, me too.
I think my guess is way off. I think my guess is going to end up being way off. Because now I'm going to go ahead and divide by 0.416, by negative 0.416, divide by 0.416 negative. I'm going to get negative 607685 units in joules per mole. When I convert this to kilojoules, 607685, yeah. This is going to be negative 607.7 kilojoules per mole. Way higher than my guess. Way higher than my guess. So my guess for that part A was way off. I don't know, is that the right answer?
Yeah, around 600, yeah.
Okay.
605.
I mean, you got, is it right on?
Yeah.
Cool, okay. Now we're going to use that 607. Oops, that was bad. We're going to use that 607.7, and we're just going to redo the problem. So part A, we've now got an answer. And now we're going to do part B. I'll switch colors to make it more obvious. We're going to do, and again, we're just going to plug in our numbers. No, we'll just do 6. I'm going to go with my rounding. I don't feel like keeping all those sig figs. Plus, it would be kind of incorrect. I converted from kilojoules to joules because I know that my R is in joules as well. So I'm going to go ahead, I'm going to calculate this side, divide by that number, and see what we get. I'm going to do 4.9 divided by 60 times 607,700. We have 49 something, divide by 1250, divide by 4.184. And I'm going to get T final minus 25 is equal to 9.49. Assuming I didn't make any typos. A little bit of rounding, right? That should be 607,695, but I did 607.7, close enough. I'm going to add the 25 over. T final's 34.5. My second one, my guess was a little bit better, right? For a rough estimate without doing any of the calculations, pretty good rough estimate. My first one was bad. This one's a little bit better. Questions about that? Again, the math, once we do the concept work, is not that hard. It's addition, subtraction, foiling, and all that stuff. It's the figuring out what do we do. So paying attention to those contexts of the problems. Delta T's, we really only have one thing we do with delta T right now, and that's MC delta T. If I've got a T final, T initial, if I'm given a constant temperature, if I'm just told the temperature is 25 degrees, whole lots of things could be going on. But if I'm told the temperature starts at 25 and changes to something else, that's a delta T problem. We're probably doing calorimetry. It's the only thing we really do with delta T. Right? And so having that kind of library of, oh, I see this situation, I kind of know what's going on mentality is a really nice thing to have. Questions?
I think like where I was confused is that when it said like molar enthalpy, like I thought that I was supposed to use like the thermodynamic table and like look at all like
Yeah, right. So same thing, right? We've got all of these different ways we can find delta H. We've got all of these different ways we can find delta S or delta G. And we have to pay attention to which context are we doing it in, right? Because theoretically, we could just go look it up in a table and figure it out. It wouldn't be relevant to this data we're given, though, right? And I will often do problems because I don't want, like I can't just, well, I could, but I don't just give data that exactly matches the theoretical, because then you don't have to do the work. You just go look it up in a table and you're like, oh, here's the answer. You can just look up the enthalpy for combustion for these. There's a huge table. Enthalpies of combustions are well documented. So I have experimental data that's randomized a little bit to make it so this number is probably not going to match perfectly. It's probably in the right ballpark, but it's not going to be exactly the same. So if you just went and looked up the value, it's not going to be the same as this. But it's going to be close. And that's the idea of, like, given this experimental context, what are we doing? Now, if I didn't give you any of that and I just said, hey, what's the delta H for this reaction? I'd probably say, make sure you use the Appendix G or the CRC handbook, but I'd still give that hint of, like, use the tables. So we have to look at what's given in the problem, and is Dr. Erker being a jerk and giving you information that you don't need when you could just look it up? Or is it asking you to do it in one of our other techniques? Okay. Now we are going to do 3.2. Let's do 3.2 number 10 first, and then we'll go into an entropy monologue. Because I think 3.2 number 10 might give us a good, like, segue into discussing entropy. This purple ink. That was not on the board very well. The purple ink doesn't erase well. It's very pretty, but it drives me crazy. Okay, so we're going on to, we did number 26, that's what we just did. 3.2, number 10. Number 10, what's number 10 say?
It says, for the process shown and using no other resources, give the sign for the entropy of the system surrounding universe, the enthalpy, and the Gibbs energy, whether it's positive, negative, or. And then for the reaction, H2O liquid goes to H2O gas at 80 degrees Celsius at 1 atm.
Okay, so maybe I will go into an entropy tirade first, because what is entropy even talking about? We didn't spend a lot of time talking about systems surrounding universe. We really, all of the entropy we talked about was entropy of system. The entropy of surrounding and entropy of universe, those are kind of like bigger conceptual ideas that frame the idea of entropy. So I'm going to do a little entropy sidetrack real quick to help out. And then we will go back to that problem. Whoa! Let's not do this. What is this even? Oh, this is 129. That was for somebody else. Okay, so what is entropy? I have taken to thinking about entropy in 3 different ways. Oh no. I've taken to thinking about entropy in 3 different ways. There is the definitional ways. Right, so how it was first kind of like written down. Then there's the kind of conceptual, and then there's the practical experimental. So for the definition, there's kind of 3, there's really 2 equations, and then there's a third that's a consequence of it. But the 2 definitional are entropy is equal to Boltzmann's constant times the nitrolog of the number of microstates. And if you ask me, that really doesn't help us understand entropy that much, right? It's introducing all of these different ideas kind of all at once. This is really just a proportionality equation. Boltzmann said, hey, entropy is going to be proportional to this idea of how many ways it can arrange, how many ways the energy can arrange. He tried to do it linear, and so he had a proportionality constant. He tried it linear, he tried it quadratic, he tried it exponential, he tried it logarithmic. Logarithm fit. So he did some experiments. He's like, hey, this fits the data. He wrote this down. He didn't, like how we use that to explain things. He's like, this is what we observe for this definition of entropy. Now, the other way we can look at it is we can get the change in entropy of a reaction or a process is going to be equal to this. Whoa, that's not how you draw sigma. We're going to have the exact same equation, no, almost the same equation we had for our delta H. Sum of products minus sum of reactants, where we take those molar coefficients into account. Here, N is the molar coefficient of each product. Here, M is the molar coefficient of each reactant. So we can just do it from the tables like we did for delta H. That also works. Nice definitional way. If we've got the number of microstates, we plug it in, we get the value out. If we've got a table, we balance our chemical reaction, we plug it in, we get it out. That's definitional idea of entropy. The last kind of definitional idea of entropy is that the change in entropy is going to be related to a reversible process divided the temperature at which that reversible process is happening. Right? This is part of how you get the units that we talk about. Now, reversible process can mean a lot of different things. In chemistry, the really useful reversible process we talk about is going to be like melting phase changes. You know, you can melt a solid and then you can refreeze it, and you can kind of do that back and forward kind of perfectly. Taking a liquid, boiling it, and then condensing it, boiling it, you can kind of do that backwards and forwards perfectly. So we use this, and we can get to this idea that our delta S for a phase change would be the delta H for that phase change divided by the temperature at which that phase change is happening. So we could do this for water freezing at 0 degrees Celsius or melting at 0 degrees Celsius. Oh, no, I did that right. I keep thinking I did the problem wrong in class yesterday because I keep thinking about boiling instead of freezing. I did it right. We did it at 0 degrees. We did it for 6.01, right? So we can just, these are really like numerical and mathematical. This is the definitional kind of understanding. And a lot of classes and a lot of things start with this definitional understanding, which honestly, after looking at this for 10 years, I'm like, I don't think it really helps us understand entropy, if I'm being honest. I feel like the idea of microstates does help us, right? One of the big problems, I really got to get that jar of marbles. One of the big problems people usually have with entropy is they associate it with like chaos or disorder or randomness. And none of that's really right, but it's not totally wrong, it's just inaccurate. It's like, it's just not quite right. And fundamentally, when you start thinking about how would you measure randomness, how do you measure random? When you think about it, it's okay, you roll dice. How do we say rolling dice is random? How do you measure that randomness? Well, you say what options you have, how likely the options are to come up. You essentially start counting how many ways can it happen. That's getting at the number of microstates. So rather than being like, it's random, we just say, how many ways can it happen? We're going to keep track of the number of different ways that it can happen. That's our number of microstates. The place where it starts to look random, what's your major?
Biomedical engineering.
Okay. So have you talked about entropy in bio classes? Okay. You will eventually. And they'll just say it's randomness. And I'll throw something on the ground and be like, that's not right. But it's pretty close. Because when we start talking about, like when we're talking about rolling dice and you're rolling 2 dice, you got like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You got a certain number of options. You never roll a 1 if you're rolling 2 dice because you can't have like one of the dice be a 0. Right? So you've got some number of options in there. If I'm rolling a dumpster truck load of dice, and I just dump them all out, I dump, let's say it's 5 million 6-sided dice. What are your possibilities? 5 million up to 5 million times 6.
Yeah.
It's a crazy number of possibilities. What is that? 5 million to 30 million. When we start dealing with numbers, and when we do this in chemical systems, it's not 5 million dice, it's 6.02, 2 times 10 to the 23rd dice. When we start getting that number of options, even if you imagine rolling 30 dice, it starts to look quote unquote random to us because our brain can't keep track of the number of options anymore. It's not actually random, it's just more than we can keep track of. And then when we can't keep track of it anymore, we're just like, oh, it's random. It's not random. We can keep track of it. There's a certain number of microstates. There's some entropy associated with it. Now, I've also got this conceptual way. I'm even reluctant to record this and put it on the internet because, like, this is a way that I think about entropy in context of chemistry that is not technically right in terms of the definitions or the experimental results we're going to look at, but I think it makes it more approachable. And when we start looking at where entropy shows up, right, we have this of how much leftover energy do I have in a process, right, the Gibbs free energy. How much energy do I have after something happens? Now, in some magical alternate universe, there's no such thing as entropy. My delta H completely tells me what's going to happen. Anything I get out of my delta H is extra energy I get to use. Anything that's exothermic will happen. Anything that's endothermic will not happen. But we know that's not true because there's all of these things that happen. And so I'll do it this way. There's some additional cost for that free energy. And that's where the T delta S comes in. And what this T delta S does in terms of this equation is it says, hey, there's some cost that we have to take out of your energy or get to put into your energy depending on the surrounding environment and this entropy idea. And for me, this kind of says, look, there's a cost to keeping energy dense. There's a benefit to spreading energy out. And this is where it becomes really cool, right, for me. One of the things that I said that nobody questioned the first week of class is I said, look, Qin equals negative Qout. Right? Any problem with that? You take a hot piece of metal, you put it in cold water, the hot metal cools off, the water warms up. Totally makes sense. Why does it do that? Why does energy leave the metal? It's a weird thing to think about, right? This is where entropy really was first developed, is like, we all see it happen, we have this experiential knowledge, we don't question it. We always grew up, hot things cool off, cold things warm up, right? We just see it happen. But when we start asking, why does it happen? It becomes this interesting idea of like, well, why does it happen? And that's part of where entropy comes in. Entropy essentially is this driving force that causes energy to dissipate. It causes energy to spread out. We want to increase our number of microstates. So for this reason, we have the first law and second law of thermodynamics that says universally entropy is always increasing. Energy is always trying to spread out. And so entropy becomes this mathematical conceptual explanation for why energy spreads out. Which, for explaining why energy spreads out, is like, okay, that's cool. But the place where it becomes useful in that way is we can start to use entropy to explain experimental phenomena. Once we get this kind of definitional microstate idea of entropy and this kind of conceptual of energy dissipating, increasing microstates is better idea, then we can start to look at experiments and say, oh, instead of measuring delta G and delta H to find delta S, which is what we did in our first lab, we can start using our experimental knowledge of entropy and our experimental knowledge of enthalpy to predict whether something's going to happen or not. So by understanding entropy better, we get this great predictive tool we've never had before. And that, for me, is where entropy is actually useful, is like the predictive tool of experiments. So in our experimental, we get really predictable things. I'm using shorthand for these. I've got them in the lecture slides, you can go look at it. But we essentially end up with some really predictable processes where we see entropy increasing. If we go from a pure solid to a pure liquid, entropy increases. If we go from a pure liquid to a pure gas, entropy increases. If we go from some reactants to more moles of gas as products, entropy is increasing. In each of these cases, we can understand it in an energy dissipating way or a microstates increasing way, which is to say, solid is stuck together, liquid is more moving around, there's more ways to organize, there's more microstates. So increasing microstates, entropy goes up. The other one that's really important is if we go from ions to an aqueous ion solution, that's actually going to have a decrease in entropy because the water molecules surround the ions. This is part of what makes it really difficult to predict what's happening in ionic compounds, because we've got this idea of the solid breaking apart, which is an increase in entropy, but then we've also got the water surrounding the ions, which is a decrease in entropy. Those two things fight against each other. Now, part of what we didn't talk about, so that's kind of the brief, that's kind of a lot of what we did in class yesterday. There's a little bit more we did in class than that, but that was kind of like the big thing, is trying to understand entropy. Some of the things we spent very little time on, delta S of the universe is increasing. We can't have, the universal entropy is always increasing for any process that's happening on its own. So when we come back to this, okay, so now I think we can go back to that problem. Okay, so we're looking at liquid going to gas before the boiling point. We still have liquid going to gas, so I think that's going to be delta S, the system is going to be increasing, right? Because I'm going from a liquid to a gas, that's just entropy's increasing. Now, this is weird. Okay, so the textbook does something weird with entropy that I'm not used to seeing, where it talks about the delta S of the universe being positive, negative, or zero for something that's spontaneous or non-spontaneous. Right, water doesn't boil on its own at 80 degrees Celsius. That's kind of weird. How do you make water boil at 80 degrees Celsius in 1 atmosphere of pressure? That's not going to happen. So I think we say in this situation, in order for that to happen, and again, I'm trying to go off of what the textbook does, that might be negative there. Because we don't see it happen. Anything we don't see happen, right? Saying that delta S of the universe is negative is like saying, hey, that's impossible. So how do we have this impossible thing happen? Well, that means that delta S's surroundings probably also has to be negative and has to be bigger. Because we end up with this thing where delta S universe is equal to delta S system plus delta S surrounding. Now, I'm trying to do this in the context of the textbook, because I know the textbook has this chart where they talk about the delta S of universe in the 3 cases. Spontaneous, equilibrium, non-spontaneous. And this would be non-spontaneous, essentially doesn't happen. I don't spend a lot of this. That's essentially how the physics department talks about it, how people in physics talk about it. I always like to talk about it in terms of product favored, reactant favored, delta S of universe is always greater than 0. Because we only want to talk about things that actually happen in chemistry. But from a conceptual standpoint, I think it does something like this. What other things does it ask us to define?
The enthalpy of the system and the Gibbs energy of the system.
Okay, enthalpy of the system. I have a hunch. So, again, I'm going with my hunches, trying to do it in the way that I think the textbook would be asking. and it's putting a bad taste in my mouth because I never like writing delta S of universe is negative. Right? I just say it's an impossible process, but I know the textbook does that, so I'm trying to be consistent with the textbook. Delta H, we can do our thinking. You missed some of this as well. The other thing we did was we said, hey, we can predict delta H's for different processes by looking at the IMFs and how the IMFs change from our reactants to our products. So I can look at this and say, do I have more IMFs in my reactants or more IMFs in my products? How many IMFs do we have in a gas? Do you know? Ooh, are the molecules interacting in a gas?
Not really.
Not really. Our ideal gases are completely spread out from each other. There's no intermolecular forces. The gas particles are too far away. Like one over here, they're not really interacting. In a liquid, they're close enough to each other that they can have that dipole-dipole hydrogen bonding force and everything. So if I'm going from IMFs that exist to IMFs that don't exist, I'm doing, I have to put energy in order to make that happen. So I think the delta H for this is going to end up being positive. I'm liking this. I think this will work out okay. Right, because I have to put energy in to break up those IMFs. The delta H of the gas is going to be smaller than the delta H of the liquid, so when I do product, why does this keep messing me up? Oh, right, okay, because I'm forgetting Q and Q. I'm forgetting a negative sign, Q and Q out. I have to put energy in to make this happen. Okay, so in this situation, if I'm looking at the delta H of the system and the delta S of the system, I'm at 80 degrees. I think the delta G should end up also positive, because this should be a non-spontaneous process at 80 degrees Celsius.
It says at least one is incorrect.
Oh, man. Okay. Okay. I got to fix my question mark, because it turns out I did not make the problem the same way the textbook did. Right? So this whole idea that delta S of universe is, negative, the textbook talks about that. I don't like it. Delta S of universe should always be increasing. That's like the second and third law of thermodynamics put together. Entropy should always be increasing in the universe. Delta S surrounding has to be opposite of the delta S of system, so that way that's the way you get that. But the delta S of system has to be more than the surrounding for the universe for it to be even possible. Your follow-up question is, how can I tell that it's spontaneous or non-spontaneous? Does water boil at 80 degrees?
No.
Nope, that's it. Right?
Okay.
It's not going to happen. So I know that it's non-spontaneous.
Okay.
It's not going to happen. Is there weird things I could do to make it happen? If I change the temperature, but it's not going to happen at 80 degrees. Right? Water, and this is kind of one of those funny things, right? In the past, I would write something like, right? Does H2O go from liquid to gas spontaneously?
Yeah, it could.
Yeah, it could, right? It's a kind of silly question to ask without more context, without knowing the pressure or the temperature or anything else. We really can't say, right? We don't know what's going on with. Do we see water just evaporate? Yeah, we do, but that's because it's forming some equilibrium with the air around it, right? But it does it only a little bit. Do we see water boil? Yeah, but not without extra information. So we usually need some other context to tell whether a process is spontaneous or non-spontaneous. We could, if our delta S of system is positive or our delta H is positive, that's kind of a tricky one, right? So if we've got delta G equals delta H minus T delta S, and we know delta H is positive, but delta S is also positive, delta G could be positive or negative, or zero, right? We could flip through all three of those. Different temperatures would make it positive, different temperatures would make it negative, different temperatures would make it zero. So there's some temperature dependence there. And so we say, oh, do we know at temperature where delta G is going to flip? Where does water boil?
100 degrees Celsius.
So at 100 degrees Celsius, we're going to see this delta G switch to like 0. And then if we're at 1.000001, it's going to switch to negative. It's going to become a spontaneous process. So we can start to see how environmental temperature or applied temperature starts to change, starts to make things happen. Any of you ever put batteries in the freezer to make them last longer? No. Ask your parents about it. They might do that. If you have batteries sitting out on a shelf, just temperature around them, they slowly start to decay. You put them in the freezer, they last a lot longer. And you don't have to worry about freezing them and exploding because of what we're learning about tomorrow, colligative properties. Questions about that? Again, this delta S universe, how you read it in the textbook versus how most people think about it. Like, there's a table in the textbook I'm not happy with. I get what they're trying to get at, but I always think delta S, like the second and third law of thermodynamics together says delta S of the universe has to always be increasing for any process we see happening.
Okay.
So just assume it's going to be increasing.
Yeah, that's kind of one of the fundamental definitions. Universally speaking, right? Locally and in the surroundings, we can have different things happen, right? We could have a decrease in entropy locally as long as the surroundings is increasing. Questions about that? Okay, we're at the end of the list. I'm going to go ahead and pause the video again and see if anything else comes up. Okay, a couple more problems to do. We're going to look at quiz 2. We're going to look at number 1 and number 3 on quiz 2. We'll start with number 3 because you asked first and you just got here. So that was your question, right? Quiz number 3. Quiz 2, number 3. Okay. What does your quiz 2, number 3 say?
Okay, we mix 35 milliliters of 0.478 molar hydrochloric acid with 80 milliliters of 0.503 molar calcium hydroxide. They're both at 21 degrees Celsius initially. What is the final temperature if the delta H of reaction is negative 113 kilojoules per mole?
Let me see something in your answer real quick. I'm curious. Oh my goodness, you did the thing.
Oh no. What?
I think you just forgot a negative sign. So I looked at your answer, and I saw that you had an answer of, what was it, 19?
0.04.
Exothermic reaction made your temperature go down?
I see.
Right? So right away, as soon as I see that, I'm like, huh. So I'm going to guess you should have gotten us down by 2 degrees. I'm guessing your answer should have been 23. And you just forgot a negative sign.
Wait, can you reevaluate it, or will it tell you?
Well, let's, you cannot, but I can, so we'll check it. But let's do the calculation together and see what we should have gotten. So I'm willing to bet that you did most things correctly. Our limiting reactant is going to be the HCl. I can tell right away. So I'm just going to do 0.035 times 0.478. That will get me my moles of reaction, because it's going to be 1 mole of HCl, or it's going to be 2 moles of HCl per reaction, right?
Shoot, I kind of forgot the balanced equation was.
So let's write down the balanced equation before I mess it up. I thought I could do it faster. So we're going to have 2 mole, sorry, I don't need to write moles there. 2 HCl plus calcium hydroxide goes to calcium chloride plus H2O. We're going to make 2 H2O for each of those. I can tell by inspection, smaller number, need twice as much. I can tell my HCl is going to be limiting. So I'm going to do 30.035 liters. I'm going to write my units because I'm going to mess it up if I don't write my units. Times 0.478 moles HCl per 1 liter. That will cancel out my units of liters. And then I'm going to do 1 mole of reaction. Wait, no. Do I need to do this? 2 moles HCl. I think I need to do that. I'm messing with myself with the delta H of reaction times negative 113 kilojoules per mole reaction. That will get me my energy out from the reaction happening. 0.035 times 0.478 times 113 negative divided by 2. I'm going to multiply by 1,000 as well. So I'm going to get negative 945.2 joules of energy. Does that sound familiar?
I think so.
Okay. Did you have it as negative? The negative's okay there. Then we're going to set that equal to MC delta T.
And for stuff like this, do you just always assume that it's like water?
Yeah. Yeah. Right, it's reacting to form water, the calcium chloride. Here's my logic for it. If we take our calcium hydroxide, let's say, and we say how much calcium hydroxide is in this 80 milliliters of it. We're going to do, let me just do a quick calculation. I'm not going to do a calculation. I know how to do it for sodium hydroxide because I did it earlier. Times, let me think, what is that? That's going to be 17 times 2 is 34 plus 40. It's going to be, what's 34 plus 40? That's 74.
Yep.
Times 74. So 2.9 grams divided by the density.
So even if the joules on the outside is already negative, you have to negative the negative?
When we set them equal to each other, right? So first, to answer your question, do we assume it's water? Out of this 80 milliliters, the part that is calcium hydroxide would be 1 milliliter. So 79 parts water to 1 part calcium hydroxide.
Okay.
So we say, that's pretty much just water.
Okay.
Right? And so the calculation I just did was like a density to volume calculation, a moles to mass to using density to volume, approximating like this is pretty much all water. Is it perfectly all water? No, maybe for our C we should use, instead of 4.184, we should use 4.189. Right, but it's going to be pretty much the same. Now, the place where do we still need to negative the negative, right? This is equal to our Q out. MC delta T is equal to our Q in. The place where I need to flip my sign is when I set these two things equal to each other. My negative Q out is equal to my Q in, so I end up negativing that negative.
Okay. See, I just took it as it was negative, and you don't have to negative the negative. You just like
you
it
have
just
to
already
negative the
is,
negative,
yeah.
right? So this exothermic process is just exothermic for that one little corner, that 1 milliliter. The way my brain thinks about it is that 1 milliliter where the calcium hydroxide is. Like my brain actually thinks about it this way. Right? Here's my beaker. Let me change colors. It's all water. 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 Down in this corner, there's this one little corner where the reaction is occurring. And that reaction is going to put energy out into the water. So this exothermic process, negative, is endothermic to the water.
Yeah.
So that's where we have to negative the negative to make it positive.
Okay, that makes sense. And then for the MCAT, is you add the 35 and the 80 together, right?
To get the total volume for the total amount of water, because both solutions have water in them.
Okay.
So we're going to do 35. So let's go ahead and finish this up real quick. Our MC delta T is going to be 35 plus 80. That's going to be 115 times 4.184 times our delta T, T final minus 21. That's going to be equal to are negative 945, so that's going to be equal to 945.2. That energy is going in. So we do 945.2 divided by 115 divided by 4.184, and we get a 2-degree increase instead of a 2-degree decrease.
Okay, that makes sense.
Right?
Yeah.
And as soon as I saw your answer, I was like, oh, I know what you did.
Yeah.
I should add something in to give partial credit if you do that, because it's a really common mistake. And there's 2 problems where that happens. There's also problem 1, this happens. People forget their negative sign. So if I finish this off, I'm going to do plus 21, and I get 22.9. If I do minus 21, negative plus 21, and if I do it exactly the opposite direction, I get 19.035.
Okay. Yeah.
So just that negative sign.
Yeah.
I think, I'm not going to say it on recording, but I'll say something after we're done. I'll just say it. I think I'm going to regrade this quiz after I add in partial credit for number 1 and number 3.
Okay.
And change everyone's points, only going up, not going down.
Okay.
So if you just forgot the sign flip, maybe I'll give you, like, how much should I give you? 1/4 point?
Probably
Still?
all of it.
I'll do a 1/2 point. Right? Maximum 1/2 point. Because, like, if you think an exothermic process is going to make your water get colder,
Yeah, I know. I should have just looked. Yeah.
right? The
Logically
nice thing
doesn't make
is,
sense.
here's the nice thing, is if that's your only mistake, when you get to the end here, just change that
Just
to a
change that,
positive,
yeah.
and
You don't have to
everything else
redo
is,
the
you don't have to
whole
redo the whole
process.
thing. All of your logic is fine, all your numbers are fine. It's this last step where you're dividing before you add the 21 over, change your sign.
Yeah.
So it's actually really easy to fix, but not fixing it looks like a fundamental misunderstanding of what's going on.
Mm-hmm.
Let's see if that's what happened in number 1. Were you number 1 or you? Let's see if that's what happened in number 1. Okay, if I erase this, you were number 26. Whoa, that's weird. Okay. See, I'm good. The thing that was weird to me that I just realized is we did 2.1 number 26, 2.2 number 26, and we're going to do 3.1 number 26. Number 26 was tricky this quarter for some reason. Okay, so let's go ahead and do quiz 2, number 1, and see what's going on. Sorry. I was just thinking I don't have time to do that quiz thing. But in any case, quiz 2, number 1.
It's a solid sodium hydroxide is added to 55 milliliters of water in a foam cup and is stirred until it dissolves. If 1.08 grams of the solid are added and the initial temperature of the water was 20.6, what is the final temperature of the water? And the enthalpy of solution is negative 44.51 kilojoules per mole.
So, what do we do? Equals?
Equals n delta H.
That's it. Oh, except equals?
Negative n delta H.
Right. So we're going to have essentially a Q in is going to be MC delta T. Our Q out, right, is going to be this exothermic part, N delta H. And when I set them equal to each other, I have to do Q in equals negative Q out. So I can go ahead and just start plugging in numbers. What was your answer?
I got 15.377.
Same thing,
Is that
right?
actually?
Your exothermic process made the temperature go down. Does that make sense?
Yeah. Should go
So my guess is the answer, you went down by about 5 degrees.
Yeah.
I bet the answer is going to be 25. Let's check. So MC delta E equals N delta H. We've got 55 milliliters. That's going to be 55 grams times 4.184 times our delta T, which is going to be T final minus 20.6. That's going to be equal to N delta H. We're going to have 1.08 grams divided by the molecular weight of sodium hydroxide. I need a periodic table for that. Hydroxide is going to be 16 plus 1 plus sodium is 23. 16 plus 1 is 27. That's going to be 40. 23 plus 17. And I'm just going to go ahead and real quick do the negative 44500, just converting it to joules per mole right away, so I don't mess up my units. And for fun, I'm going to leave off the negative. I'm just going to put a little note here, like, right? I'm doing this on purpose to see if we get the same answer, and we'll see how we can fix it quickly when we realize we made a mistake. So I'm going to go ahead and plug in all of my numbers. I'm going to do 1.08 divided by 40 times 44500 negative divided by 55 divided by 4.184. And I'm going to get T final minus 20.6 is equal to negative 5.22. I'm then going to just add over that 20.6. And I get 15.377. Now, if I remember that negative sign, I just erase that. And I do 5.22 plus 20.6, and I get an answer of 25.8. Just that negative sign. Very common mistake. I mean, you all saw me how often it was easy for me to forget that negative sign when we were doing this. Fortunately, I had all of you being there being like, hey, don't forget your negative sign. Actually, most of you forgot it, and it was only when I started doing calculations that I was like, wait a minute, why didn't anyone stop me? So yeah, number 3 on quiz 2 and number 1 on quiz 2 both have that Q in equals negative Q out. And if we forget that negative sign, our temperature goes in a non-intuitive way. However, if we slow down and think about it, we say, oh, wait, that doesn't make any sense. My temperature should not go down when I'm doing an exothermic process. It should go up. And if that's our only mistake, I will say, the student who brought this to my attention yesterday in office hours, on number 1, it was just the negative sign. They went down by 5 degrees instead of up by 5 degrees. On number 3, we were like, oh, I bet it's the same thing. They were like, we don't know what their mistake was. It was off by like 30 degrees. So my guess is like a wrong molecular weight or wrong limiting reactant or wrong like something else was going on. But also it was going down instead of up. So it was something else wrong plus they forgot their negative sign. Questions about that? Pretty straightforward. Just don't forget your negative signs. 3.1, number 26.
It says a process increases the entropy of a system by 811 joules per mole Kelvin and absorbs 73.9 kilojoules per mole of heat from the surroundings. At what temperature will this process begin to favor products?
Does it just give joules per mole? Kelvin?
It just says kilojoules per mole.
Oh no, for the delta S. Joules per mole Kelvin. It looks weird because it's just like a space and then the K. But our units. Okay, so we've got our delta S, we've got our delta H. Endothermic process because it's absorbing from the environment, so it's getting energy put into it. Delta S is positive because we're increasing our microstates. And again, for these problems, I like to explicitly, I know we assume if there's no sign there, it's positive. For these things, I like to explicitly write my positive signs because the sign of these things is so important. I want to make sure I didn't like accidentally forget a negative sign. I want to be like, no, this is intentionally positive. It's not like I just forgot a negative. So what we've got is, oh, what's the question?
At what temperature will this process begin to favor products?
Okay, so at what point, there's missing information, right? And every problem has this. What tells us if we're favoring products or reactants?
The G.
Yeah. We're going to have this delta G equal delta H minus T delta S. It's also asking temperature, so we figured we need an equation with temperature in it. At what point is, what value of delta G is favoring products?
Positive?
Ooh.
Negative?
Negative. Negative delta G favors products. What delta G favors reactants?
Positive.
What delta G would be changing that?
1 and 0.
Yeah. So we want to do this one. We want to do when delta G is equal to 0. So we have 0 is equal to delta H minus T delta S. We just get delta H is equal to T delta S. And now we solve.
Okay.
I'm going to go ahead and do some unit conversion. We're going to do 73.9 is equal to T times 0.811. 73.09 divided by 0.811. That should be it.
Okay.
Right. Notice again, the math we end up doing, super easy. Right? The math is not the hard part in any of these problems. Even though everyone gets obsessed with like, oh, I got the wrong number. How do I get the right number? I just keep changing the numbers. So 73.9 divided by 0.811. 91 Kelvin. Man, 91 Kelvin. That's a really low temperature.
Isn't it negative delta H equals T delta S?
No, it's delta H equal as, no, you can see it it would be like negative delta H equals negative T delta S. I dropped the negative from both sides.
Oh, okay.
Right? Or you can see it like I added the T delta S over and then flipped it. Like, I'm freaking out a little bit because that's such a low temperature. 91 Kelvin. It's a really low temperature. That's like that's like a little bit above liquid nitrogen, which is 77 Kelvin. It's cold. Yeah, so again, mathematically pretty easy. Conceptually, a couple things we have to watch out for. This idea of when is delta G, like the fact that we're using this equation to figure out whether it's spontaneous or not, product favored or reactant favored. The conditions of delta G that give us that and where it changes. And then just setting it equal to each other, making sure we do our unit conversion so that we're in the same units when we do our calculation. Get an answer in Kelvin. Does anyone want to do number 26 on 3.2, just so we can do all of the 26s? Are there even 26 questions on that one?
I don't think.
23.
Ah, okay, I guess that'll be it then. Okay, so we had a question. We're doing some concept questions. We're kind of done with homework questions. But someone really wanted to, we have this question. What is delta H of reaction versus delta H of formation? We'll do standard. This superscript 0 is going to become more and more important very soon. Delta H of formation is a special reaction. So technically, delta H of formation is a delta H of reaction, but only for a particular thing. So this is key terms and definitions, right? Why don't we just say delta H for one thing versus delta H for another thing, right? The subscripts are there to help point us towards the right idea. Delta H of reaction just means we're doing it for a chemical process going from reactants to products. It could be anything, any reactants to any products, it works for anything. Delta H of formation has some extra specifications on it. Delta H of formation is right. Delta H of formation is a specific reaction for the material. It's the pure element to 1 mole of product. So if we wanted to look at the delta H information, I'm going to pick a weird one. Let's say this was in an earlier problem. We want to get the delta H information for acetic acid. Well, I look at this and I say, well, really, if I wanted to look at this from a chemical standpoint, I'd probably put some methyl group together with some other things, like all that. But from a delta H formation standpoint, I'm going to have carbon solid plus O2 gas plus 2H2 gas. Right? I'm going from my pure elements. I put pure in quotes because the diatomic gases. That's going to be, I got to do 2 carbons. 2 carbons, 2 oxygens, 4 hydrogens. That's going to be my delta H formation for this. It's a particular reaction, very specific reaction. And it's this idea of trying to get like how much energy is embodied in this molecule. How much energy does that molecule carry around as we look at it? So that's the difference between delta H of reaction versus delta H of reaction. Technically, you could write down delta H of reaction for this and you wouldn't be like fully wrong, but you could be more specific. And we'll notice that in problems, there are problems that are specific, like, oh, I want the delta H of formation. I want this particular reaction. Okay? What was your question?
Okay, this is going back to ice again.
Yeah.
But let's say you have like ice that's like at like, I don't know, like negative 20 degrees, and you put it in warm water. Would it be, you would need to take the Q of the ice, the MC delta T from the ice getting from negative 20 to 0?
Mm-hmm.
And then you would take the N delta H of it going from solid to liquid.
Mm-hmm.
And then you need to take another MC delta T from
Possibly.
liquid to, or from when it's warming to when it balances with the other water.
Yes.
Thank you.
But then what does that equal to? Is that equal to the water heating up? Or cooling down, I mean?
Yeah, so essentially if we are putting it in warm water, assuming that the all of the ice melts, our Q in process is going to have 3 Qs associated with it. Warming the cold ice, melting the ice, warming that melted ice.
Okay.
Right? While the water is just giving up energy, our Q out is just one thing giving away that energy.
Okay. Okay, that was,
So yeah.
I just didn't know if there was going to be 3 or you combine the Q of the, once they both become water, if that's just one Q or they're on opposite sides.
I've seen a couple students, I don't know where they're getting this. I don't know if like Khan Academy does this or if there's some online thing that does this, but I've seen several students that are doing this like combination of like, they're essentially doing these 2 Qs versus this Q, they're getting an excess Q, they're doing this weird subtraction, they're doing a mathematical process that I haven't really seen before.
Mm-hmm.
That kind of works out eventually, but for me, loses track of the physical reality of what's going on.
Okay.
It makes energetic sense, but it loses track of what's going on.
Okay. Okay.
And so I don't even want to do it. It does work, it does get the right answer, but it does it in a weird way. And I can explain it, right? So essentially we've got an MC delta T, we got an N delta H, and we got an MC delta T, and we've got an MC delta T. And essentially what they're doing is they're adding together, right, this MC delta T. Since they have the same C's, you can kind of add them together, but not really because their delta T's are different. But if you write these MC delta T's, instead of writing it like that, if you write it as MC T final, T initial is 0, so that goes away. And this is MC T final minus MC T initial. You can essentially add this MCT final to that MCT final. You add the masses together. It works, but it's just kind of, it's mathematically correct. You just lose track of the physicality. And I find the physics of it, the physical setup of it, the chemistry of it, really helps me make sense of what's going on.
Mm-hmm.
This works mathematically, but you lose sense of what's happening physically.
Mm-hmm.
So I've seen people do it that way, but I don't prefer it. You still get the right answer. You just have to be careful. The place where I've seen people make the mistake is they add it together and they don't recognize that these delta t's are going to be different. And so then they just add them together, they calculate delta t, and then they get a wrong answer because they're delta t's. This delta t, the delta t's are different.
Yeah. Okay.
T final's the same, delta t is different.
Mm-hmm. And then I was confused on how you're getting delta H when you like are looking at like a reaction.
Ooh.
What we did yesterday, like when you did the H2O
Oh.
plus NH3.
So this is not,
Or the other one.
yeah, this is not for any particular reaction. This is for the mixing process,
Mm-hmm.
right? So I have looking at a chemical reaction, if you were, I don't think you were in office hours earlier, but I did my best to predict the delta H for a reaction, and I was off by a factor. I was like, oh, I think it's 100 kilojoules. It was 600 kilojoules. I was totally off.
Okay.
Right? Predicting the delta H for a reaction, unless you've got like bond energies floating around in your head someplace, it's really hard to predict that.
Uh-huh.
But for a solubility process of two liquids, here's what we're looking at. And we're not really able to predict it very well, but I'm doing an H2O liquid plus NH3 liquid goes to NH3 aqueous.
Mm-hmm.
And what I know is that my water here has hydrogen bonding force, dipole-dipole, London dispersion force.
Mm-hmm.
So if I want to get my water molecules away from each other so the ammonia can fit in between, I got to put a bunch of energy in.
Mm-hmm.
Then on this side, my ammonia has hydrogen bonding force, has dipole-dipole interactions, and it has London dispersion force.
Mm-hmm.
So I'm going to make space. I'm going to take my ammonia molecules, which are all close to each other, and I'm going to take my water molecules, which are all close to each other, and I'm going to spread them out. Right, and the energy is spreading out 1, 2, 3, 4, 5, 6, 7, 8. My energy to spread out the water molecules
Mm-hmm.
is going to be related to the IMS I have to deal with.
Yeah.
My energy, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's just do 10. My energy to spread out my NH3s is going to be related to the IMFs.
Mm-hmm.
And now I'm going to put them back together. I'm going to say, hey, when I take these two things and I put them back together, what do I get back out of it? Well, when I look at the interactions of ammonias with water, right, here's my NH3. Well, that hydrogen is really far away. That's silly. Here's my NH3. Here's my H2O.
Uh-huh.
London dispersion force, about the same size,
Mm-hmm.
because they're the same surface area. Dipole-dipole interaction, pretty similar, because they're still about the same. Like nitrogen, a little bit weaker on nitrogen than oxygen. Hydrogen bonding force, still there.
Mm-hmm.
So when I look at this, I get back out the exact same energy.
Mm-hmm.
So
So like it's like taking energy to spread them apart, and then you're getting back that energy because they want to go back together because they have the same forces.
Mm-hmm. So if I look at the amount of energy in my products from the amount of energy in my reactants, I can say, look, this is going to be about 0.
Mm-hmm.
Because the energy I'm putting in, I'm getting all back out. My negative side and my positive side are about the same size.
But then if, let's say, whatever you add to water, like, has a lot more of one force, or like not as much, then it would be super positive? Is that
Yeah. So
because it takes a
more.
lot of energy to split up and then they wouldn't come back together.
Yeah.
Okay.
So the typical example we have for that.
I think you gave it was hexanol and water.
Yeah.
Does
So
that-
let's go even more extreme than hexanol. So this example makes sense,
Yes.
right? So this is what we call an ideal solution. Our delta H of solution going through this process. I should put products and reactants in quotes here because this isn't really a chemical reaction, right? It's a process. But when I look at what happened before the process, what happens after the process, I'm going to get about the same energy out. I'm going to end up with a 0 energy. So if instead of doing NH3, I do, I'm going to leave
Wait,
the
and
water
if
picture
the
there.
delta H is like in that one, it would dissolve, right? Like if the or does that are those
It
not
would,
related?
but why? If the delta H is approximately 0, what's going to make it spontaneous or go towards products?
Because it wants to like go together with the.
Why does it want to go together? Entropy increased microstates,
Okay.
right? Having things mixed up is more energetically beneficial than having them separate.
Okay.
So let's go ahead and do this for C5H12 pentane. And we're going to say this is C5H12 liquid, and we're going to say, I'm going to put a question mark because we're kind of questioning whether this happens or not. Do we form C5H12 aqueous? Does that happen? Now, H2O is this molecule. Pentane is that molecule. So when I look at the intermolecular forces of one pentane interacting with another, only London dispersion force. So when I've got all of my pentane molecules next to each other, 2, 4, 6, right, and then I spread them out, that doesn't take very much energy because it's very small, very weak intermolecular forces keeping them all clustered together. Now when I put them back together, and I should do something kind of weird, instead of drawing these as dots, I should draw them as kind of like little lines. Because they've got a much bigger surface area. They've got a much bigger surface area than the water molecule, right? If I wanted to draw this in relative size, I would probably draw my water molecule about that big compared to the pentane. Very different surface areas. So now when I go to put them back together, right, my water molecules don't get to be next to each other. They're not going to get any hydrogen bonding force, right? This is going to be an overall cost. I have to put energy in that I don't get back out.
Okay.
So I have to put energy in that I'm not going to get back out. In this situation, I'm going to see essentially a delta H that's positive. I'm going to see an endothermic process.
And that doesn't, so then it doesn't dissolve in water?
Not at room temperature, right? So what we're going to see is the entropy is going to prevent it from mixing. Right? So in this situation, delta H of solution is going to be positive, and we're going to put this in quotes, prevents mixing. Now, it doesn't perfectly prevent mixing. Can we do things to force them to mix? What 2 things could we do? There's 2 different things we could do.
Temperature.
Heat it up, right? Making it so that entropy term is more important by increasing the temperature, right? We can't increase, the entropy of this amount of stuff mixing is just going to be that entropy. But we can increase the temperature, which is going to multiply by that entropy and make the mixing more valuable. So that's one thing we can do. The other thing we can do besides heat it up, shake it up. Another way, just we put energy in somehow, right? So as long as we're shaking it, we can force these two things to mix, right? We can shake it up and it's mixing, it's mixing. As soon as we stop shaking it up, stop putting that energy in, it's going to start separating back out. Same thing with heating it up. Heating it up, we're putting energy in, we might get it to mix some. As soon as we stop heating it up, it starts to separate back out. Because this enthalpy term is going to dominate over the entropy term. And the reason that's generally true is because our enthalpies are usually on the kilojoule scale, our entropy is only on the joule scale. So enthalpy usually dominates. Not always, but usually dominates.
Unless it's like 0.
Close to 0, like small, unless it's small. Or the temperature is really high.
Okay, yeah, that makes sense.
Cool.
So the enthalpy in this is positive because we're forming a bond?
Well, we're not forming bonds. We're breaking more intermolecular forces than we get back. Right, so all we really get back here is...
Oh, the energy to break it is more for H2O than it is for the C5H12.
Yes, by a lot.
Okay.
But more importantly, so there's energy to push the water molecules away from each other, right? I gotta interrupt all those hydrogen bonding forces, those pretty strong forces. That takes energy to do that. London dispersion force, this is pretty easy to push away from each other. But more importantly is when I get energy back out from mixing, I'm going to get the London dispersion force energy back. I'm not getting the hydrogen bonding force energy back. I'm not getting my HBF energy back. So in order to make this happen, I have to put in more energy than I get out.
Because it requires more energy.
On this side.
Okay.
Yeah.
And our test is next week, right?
Next Thursday, yeah.
And there's an online portion too?
Yep, will just be like a quiz.
Okay.
So it's just like a cumulative quiz.
Is there gonna be like an MQ that'll like be over everything, or is it just like the cumulative?
Just look at all of them. Yeah.
Okay. Okay.
I'm gonna go
Thank you.
ahead and stop this and get it uploading.